Welcome back to Bite-Sized Breakthroughs. I'm your host, Alex Askwell. Today we're diving deep into a fascinating new paper titled Transformer2, Self-Adaptive LLMs. We're joined by Dr. Paige Turner, the lead researcher on this project, and Professor Wid Spectrum, an expert in the field of adaptive AI. Welcome both of you.
Thanks for having me, Alex. It's a pleasure to be here.
Dr. Turner, to start, can you give us some background on why self-adaptive LLMs are needed? What are the limitations of traditional fine-tuning methods?
Absolutely, Alex. Traditional fine-tuning of large language models, or LLMs, usually involves optimizing the entire model for a wide range of tasks in a single training session. While this is straightforward, it's also incredibly resource-intensive. It requires massive computational power and training time, making it quite expensive. Furthermore, there's a performance trade-off. When you add more breadth to the training data, the model can struggle with overfitting or task interference. It becomes challenging to make the model good at everything simultaneously, since increasing breadth comes at the cost of depth. We wanted a more flexible and efficient approach, mirroring how biological systems adjust to changing contexts. So the current process is a bit like trying to teach a child everything they will ever need to know in a single massive lesson, which is not how humans work. Instead, we adapt and adjust depending on the situation. That is the goal of this paper. Exactly, Professor Spectrum. We look to create a system more like modular learning, where specific skills can be activated when they are needed, rather than trying to encode everything at once. And this takes us to self-adaptive models that can dynamically modify their behavior based on the task at hand, without the need for constant retuning. This would also allow the model to add new skills over time without forgetting the old ones.
That makes sense. So what are the key contributions of your paper in addressing these issues?
Our primary contribution is the development of Transformer2, a framework for self-adaptive LLMs. Within this, we introduce singular value fine-tuning, SVF, a novel parameter-efficient fine-tuning method, which is a key ingredient for allowing our framework to function correctly. We also implement 3 adaptation strategies within Transformer2, which allow it to adapt to the input task. We directly train the SVF modules using reinforcement learning in order to directly maximize their task performance and enhance their modularity.
Let's unpack that a bit. What exactly is singular value fine-tuning, or SVF, and how does it differ from something like low-rank adaptation, or LoRA?
LoRA, which is a popular approach, freezes the original model's parameters and introduces small, trainable low-rank matrices for task-specific updates. This is parameter efficient, which makes it less computationally expensive than fine-tuning the whole model. However, the low-rank matrices introduce limitations since they do not make use of the full space of the weight matrix. The idea is that if you want to add an additional concept to your existing model, the most effective approach is not to add an extra space, but to adjust the existing space, right? And that is exactly what we do in SVF. Instead of adding new low-rank matrices, we analyze the existing weight matrices using singular value decomposition, or SVD. SVD decomposes a weight matrix W into 3 components, U, Cu, and V transposed. Cu is a diagonal matrix containing the singular values. With SVF, we introduce a trainable vector Z that scales these singular values independently, thus modifying the magnitude of the singular components. The new weight matrix U' is thus obtained as W equals U V transpose diag Z. For our listeners, imagine a weight matrix as a complex landscape. LoRA tries to add a small new hill to this landscape. SVF, on the other hand, adjusts the existing peaks and valleys, making more efficient use of the original structure.
That's a great analogy, Prof. Spectrum. And Dr. Turner, what benefits does this approach provide compared to LoRA?
First, SVF is incredibly parameter efficient because it only needs to train the vector Z. In contrast, LoRA requires m plus n r learnable parameters per weight matrix, where r is the rank of the low-rank matrices. In practice, we found that SVF required orders of magnitude fewer optimized parameters than our LoRA implementation. Second, decomposing weights into independent singular components makes the learned expert vectors highly composable and interpretable, since you can combine the different components algebraically. In LoRA, the trained parameters are far less composable since they exist within a low-rank space. Third, exclusively modifying the magnitude of pre-existing singular components, provides a principled form of regularization, helping to mitigate overfitting. This also means that it can be trained using very few samples without the risk of a collapse of performance.
So, SVF is not only more efficient, but also more flexible and robust due to its inherent modularity. Now, Dr. Turner, the paper mentions three distinct adaptation strategies used during inference in Transformer 2. Can you walk us through each of them?
Certainly, Alex. The first strategy is prompt engineering. Here, we construct a new adaptation prompt and give it to the LLM to categorize the input prompt. Then, based on its response, we choose the appropriate expert vector from the SVF-trained modules. The prompt contains categories like code, math, reasoning, or others, allowing the model to use its base weights if no expert is deemed appropriate. The adaptation prompt is given as an example in the paper. This is the most basic method, since it directly leverages the base model with no further training. Our second strategy builds on the first, using the same categorization task but through a more refined method. We use a specialized system. The way we do this is by training the base LLM itself to handle the task identification with another SVF module. This is the classification expert-based adaptation. We collect a new dataset where each sample is a tuple of the form XKK, where X is an example from task K and K is the label for the task. Then, we train the base LLM in a very similar fashion as the original expert vector Zs. This additional training allows a better selection of the appropriate expert vector during the first pass of inference. Finally, we have our few-shot adaptation strategy. This one assumes we have access to a few samples for the target task at hand. We don't use these samples to directly train the model, as would happen in traditional fine-tuning. Instead, we combine the different expert vectors using a weighted sum, z equals c key op key z z he, and then we use an optimization method called the Cross-Entropy Method, or CEM, to search for the optimal alpha weights based on the samples provided. This enables us to effectively tailor the model to the target task based on a few samples. And just to emphasize a key point, using few-shot data with CEM is different than other few-shot learning methods, since these methods usually involve increasing the length of each prompt to include a few examples, which causes them to scale poorly. In contrast, CEM decouples the length of the input from the optimization itself. All the work happens within the model weights, without modifying the user's prompt.
That's a very clear explanation, Dr. Turner. Now let's talk about the experimental results. Which models and datasets did you use to validate your approach?
We used 3 pre-trained LLMs spanning different model families and architecture sizes: Llama 3.8b Instruct, Mistral 7b Instruct VZ.3, and Llama 370b Instruct. For each model, we trained 3 sets of SVF expert vectors to maximize performance on the GSM-8K, MBPP Pro, and ArcEasy datasets. These datasets cover math, coding, and reasoning. We also trained a set of Z-vectors for vision language using the Llama 3 Lava Next 8b with the Text VQA dataset. Then we evaluated the framework on unseen tasks, namely Math, Humanival, ArcChallenge, and OKVQA. It's worth noting that we assessed the generalization by applying the language experts to the vision language task.
And what did you find, Dr. Turner? Did SVF live up to the expectations? How did it compare to LoRA?
The results were very encouraging, Alex. SVF consistently outperformed LoRA across nearly all tasks and base models. For example, with the Llama 3.8b Instruct model, on the GSM-8K dataset, SVF achieved a score of 79.15, while LoRA only reached 77.18 and the base model 75.89. Similar gains were observed across all 3 base models and tasks. Moreover, in many cases, LoRA did not improve over the base model at all, and in some cases, even degraded the base model performance, indicating that the model was overfitting. We also observed significant performance gains in the vision language domain, with SVF increasing the base model performance by over 39%. SVF performed much better than LoRA when combined with RL, confirming that SVF works much better than LoRA when it needs to be trained without a precise next token prediction dataset.
That's impressive, Dr. Turner. What about the self-adaptation performance of Transformer 2 on those unseen tasks? How did the 3 adaptation strategies compare?
We found that all three adaptation strategies within Transformer 2 showed improvements across all tasks for the Llama 38B instruct model, and in at least 2 out of 3 tasks for both the Mistral and Llama 70B models. In contrast, even the best training LoRAs only provided marginal improvements, and in some cases, it significantly degraded performance. This is especially true for the math and human evil tasks. What's also interesting is that we saw a monotonic trend. With more information about test time conditions, the adaptation was increasingly effective. In particular, the few-shot self-adaptation method was almost always the highest scoring method, and that is particularly relevant since the optimization is decoupled from the input length. For example, on the Humaneval dataset, the Llama 38B model reached 62.99 with few-shot adaptation and 61.59 with prompt-based adaptation. The classification expert was also better than the prompt-based approach.
And that highlights the effectiveness of that CEM-based few-shot approach. Professor Spectrum, what do you make of these results from a field perspective?
These results are very promising, Alex. The fact that SVF outperforms LoRA while using fewer parameters is very significant. Also, the ability of Transformer2 to adapt to completely out-of-distribution tasks, such as vision-based tasks from text-based experts, shows the framework's versatility. The few-shot strategy is also of special interest, since this is a data-efficient way to fine-tune without the need to manually expand every prompt with few-shot examples. It's exciting to see this move toward truly dynamic and adaptable models.
It's clear that Transformer 2 has a lot of potential, but what are its limitations and what future directions are you exploring?
One limitation is that the capabilities of the SVF experts are inherently tied to the latent components of the base model. We cannot introduce completely new skills without somehow modifying the base weights. We believe that techniques like model merging could help address that limitation. The CEM method also has a computational trade-off between one-time overhead and performance. While our current setup is very efficient, scaling to a large number of specialized domains might introduce increased one-time costs. Additionally, our cross-model transfer experiments suggest that our models need to have similar architectures for an effective transfer. So this is still a question for future research. And building on that, we're keen to investigate how Transformer 2 could be used in continual learning scenarios. It's critical that our models can adapt to new tasks over time without forgetting the old skills. We also aim to explore different methods for the few-shot CEM-based adaptation and explore its applicability in models with distinct architectures. There's also the idea of further improving selection strategies of experts by using heuristics, such as past performance or even token-level analysis.
Those are all very important points, Dr. Turner. In a broader context, how do you see Transformer 2 impacting the field of AI, and what are some potential applications?
Transformer 2 has the potential to shift how we fine-tune LLMs. The ability to dynamically adapt to diverse tasks could lead to more personalized AI assistants, robots that adapt to changing environments, and even AI tutors tailored to individual learning styles. In healthcare, it could enable models to combine general knowledge with specific domain expertise. Scientific discovery would also benefit, with models that adapt as new findings emerge. Moreover, our model has shown that language-based models can be adapted to vision-based tasks, suggesting its applicability in multimodal learning. There is also potential in real-time language translation by combining different language experts in a dynamic way. The parameter efficiency and small data training requirements of SVF and Transformer 2 are also important for building systems that work in low-resource environments and with limited data sets. Finally, I think that a framework like ours is very valuable for building continual learning systems that can acquire new capabilities over time, and is something that we are focusing on in our future research.
That's a very broad range of applications. Professor Spectrum, do you have any final thoughts or perspectives on this research?
I think the core ideas of SVF and Transformer 2 are a significant step forward. The focus on adapting models through principled parameterization of the existing space rather than adding new spaces is crucial. It is also important that the model can be trained with RL directly, since this unlocks applications for datasets that do not contain detailed solutions or reasoning processes. This research highlights that we should move away from treating LLMs as static tools and towards dynamic, adaptable systems that can learn and evolve in real time. This has a lot of potential to create systems that are more flexible and efficient.
Thank you both, Dr. Turner and Professor Spectrum, for this fascinating discussion. It's clear that the Transformer2 framework is a significant step towards making AI systems more adaptive and efficient. The insights from SVF and direct task training with RL could revolutionize how we approach LLM development and deployment. The composability of the expert vectors and the potential for cross-model transfer also opens the door to creating truly versatile and reusable skill libraries. For our listeners interested in a more granular analysis, the full text of this research paper can be found in the show notes.